Yeah.
Okay.
So
Now go ahead.
in lecture 2, you told that for a group of order 4, there are two possible structure of groups.
Yeah.
Uh, uh,
I said
and
that.
other,
I didn't prove
yeah,
that.
yeah, yes, sir. So I tried to find out, but I could not find out the. Actually, what I found were re-identification of the same structure, but I
Hmm.
did not find the two different structure possible.
Yeah, but
Can you?
lecture 3 is up. And lecture 3 actually gives you both the structures.
Okay. Okay.
From a different context. Lecture 3, uh, well, like lecture is it's actually possible. It's not very difficult. You should try it again, at least to do it
Okay. Okay, sir.
that way. What happened? Somehow. Okay, am I still here? Because my screen seems to have frozen.
Yes, sir.
My presentation doesn't seem to be starting somehow. Let's see what happens. Okay, anyway, until I can get the thing to start, um, the question there are okay. The way we did it, we with lecture with one element, of course, you had only one possible multiplication table. With two, it's pretty straightforward. Only one is possible. With three, it takes a bit of thought. With four, you can actually find two possible things pretty easily. It's not very difficult. But in the lecture 3, what we have talked about are things called presentations of a group, not representations, presentations. And presentations actually uh, give you another way of writing down a group. That is basically you give a small number of elements, and of course, if an element is there in the group, then any number of times you multiply the element by itself, that will also be there in the group. So if G is there, G square will be there, G cube will be there, and so on. And a group can be specified by giving a small number of its elements called the generators and specifying relationships between those generators. That's what a presentation is. And as an example, I give you a presentation which is actually a presentation for one of the two kinds of groups of four elements, the Ferrer group or the Klein four group.
Sir,
Well, actually, I seem to have been frozen out of my computers right now. So I'm using the phone. I'm trying to get back on in the system. Okay. So you can hear me,
sir,
right? Right now?
yes, sir.
Yeah. So I'll be
So
back
you
in
said Klein for group,
the client 4 group. Yeah.
C2 cross C2, is that it?
So you all heard that.
Uh,
The Klein 4 group is one example, and the other group is simply a cyclic group with 4 elements.
Yes, sir. So the Klein 4 group is C2 cross C2, right? I mean, that is
Yeah,
C4.
C2 cross C2.
Okay.
C2 cross C2 is not C4, so that's
Yes, sir.
distinct.
Yes, sir.
It so happens that both of these groups are abelian, and the group of size 5 has to be abelian, at least for those of you who have done and prior group theory course would know that, right? You would know that any prime order group has to be abelian. So the first or the smallest non-abelian group that you have is the group of order 6, which, by the way, you already know because you have seen that group. There's a group of symmetries of an equilateral triangle. I'm trying to just hold on, let me. Okay, my presentation has started, which is good, but I don't have anything to present really today. But if you have any further questions, please go ahead. Otherwise, I'm going to talk about some things which are peripheral to this course, really.
Sir.
Yeah, go ahead.
So one thing we learned about was this ON, right? I mean, a set of all orthogonal matrices. So they are real. So when we take complex entries, it becomes U.
UN, right?
So UN, right? So could you tell about UN, or will you cover it later?
I will cover UN anyway, but UN is just a group of unitary n by n matrices, right? And you can easily show that they form a group because they obey all the properties of a group.
Yes, sir.
And the details, UN, of course, especially SUN, is very important in particle physics and in lots of other places besides. So that theory, of course, will be covered later, primarily because those are infinite groups. So second half of the course, the detailed theory of SUN, or detailed theory of Lie groups, in which SUN will come in as a part.
So even SUN is right, SON. So SUN is also like SON only, with determinant 1.
Well, not really. Okay, let me just, since the question has arisen, let me just talk about something which we are going to cover in detail later, but this is an interesting topic which most of you would be familiar with even without knowing the group theoretical things. So I hope you can see the thing that I'm writing right now.
Yes, sir.
Okay, so the question that was asked is SON, or for example SO3, which we usually write as SO3 comma R, just to emphasize that these are 3 by 3 orthogonal matrices. And the question that was asked is SO3 or SU, say 3. Are they the same, or are they similar? Well, they are similar in many respects. Of course, they are groups, so they obey many of the same properties. However, there are certain very interesting things which are different, and there's an important connection between these two. So, in fact, I would have talked about this anyway today, because although this is not really what I would cover now, I will definitely talk about this more formally later. But first, everybody knows what SO3 is, right? Physically, in physics or in geometry, what is SO3?
Set of all rotations.
Yeah. So basically, okay, what you could say is all rotations can be put in 1-to-1 correspondence with a 3 by 3, with a set of all 3 by 3 orthogonal matrices. But in mathematics, very often we don't say that two things are in one-to-one correspondence so that every one of their properties match, we just say they are. So instead of saying that SO3R, the set of all 3 by 3 orthogonal matrices, is actually in a one-to-one correspondence in an isomorphic fashion. Those words will be explained later anyway. With all rotations, we just say rotations form the group SO3. There's a advantage of using abbreviated language. As long as we understand what that means, then we are fine, right? But we use it all the time. When we say a velocity, when we draw a velocity vector on a piece of paper, nobody, of course, assumes that that arrow is something which is moving, right? The arrow is just a representation. It's a way of, showing what the velocity vector really stands for. Similarly, SO3, the matrices are essentially things which represent the actual rotations which you carry out in space. Okay, but the technically important thing, this is something which all of you have covered before, somewhere or the other. If you want to describe a particular rotation, what do you need to specify? A given rotation, just one fixed rotation, what would you specify it with?
Axis and angle.
Okay, well, that's one possibility. I'm pretty sure you've already also done something else. You have done the Euler angles, right? Somewhere in classical mechanics, quantum mechanics.
Yes, sir.
Yes, sir.
In fact, I taught you
did it in
also in quantum mechanics.
Yeah,
But anyway, axis angle. I'm not very sure whether I covered this part technically. But I also perhaps talked about this also, which is one way of representing this would be give the unit vector, give the angle. But another way would be just give a vector whose length is the angle. Is that okay? If I gave you a vector whose length is equal to the angle of rotation and whose direction is in the unit vector, which is in the direction of the axis, I hope everybody is clear that this will specify the rotation. Yes?
Could you repeat that?
So I want to represent a rotation, right? As was said, to represent a rotation, I need the axis, which is a unit vector, and we need the angle of rotation. So instead of giving these two separately, I can definitely combine them into just giving you a vector whose length is theta and whose direction is the axis. Isn't that enough to specify the rotation? Is that difficult to understand? See, I'll give you
sir, if you, in the first representation, if you change theta by 2 pi, you'll end up with the same vector. But here, after 2 pi, your vector will keep on increasing.
Good. That's a very important point. But that is also, so here, what is going wrong here by saying that I can just give you theta times n hat is simply this, that even here, if I just said that I gave you n hat and theta and that will give you the represent rotation, that's fine. But then you would have to see that n hat and theta plus 2 pi would have to be the same rotation, right, as n hat theta. Which means that between the set of rotations and between the set given by this pair, the unit vector and the angle, the correction is not one-to-one, right? There are many possible pairs here which will give rise to the same rotation, right? That problem is here as well. Here, of course, what you do is you deliberately force yourself to say that theta plus 2 pi means the same thing as theta. So here also we could do something very similar. Is that the only problem? Because here what we are saying is, okay, instead of giving n hat and theta, I'm giving theta times n hat. First question, if you are given a vector, can't you find out the unit vector in its direction and its angle? Yes or no? And its length, sorry. Given a vector, can't you find out theta from it and n hat from it? That's class 11. theta. So given a vector v, isn't it possible to find the length of the vector v, which in this case is the angle, and the unit vector in the direction of v, which is simply v by mod v?
Yes, sir, but it is not unique. I mean, I don't know, but
Yeah, but neither was this. You're right. But neither was this. So this is just the first step. But you should, if you are happy with this, then you shouldn't be unhappy with this. That's my point. You may say, you may of course raise objections that this representation using the axis and the angle is not a good representation in the sense that it's at least not one-to-one. And I would agree. Well, neither is this. And I agree with that as well. All I'm saying is these two, there is no real difference between these two. Given n hat and theta, you can of course find out theta n hat. Given this vector, you can always find out theta and n hat, right? Although there is no one-to-one correspondence between these vectors and the rotations, there is a one-to-one correspondence between this and this, at least. Is that okay? Okay, let's move on. And that problem that you have raised, that this is not one-to-one, is a very important problem. But before we go there, can anybody tell me what range should I give theta? That is, theta should, given that this problem will arise, to prevent this problem, can I restrict the value of theta? 0 to
2 pi.
0 to 2 pi. That is less than or less than equal to?
I think 1 equal to should suffice.
1 equal to should be there.
Okay, good. Because what you're saying is 2 pi rotation is the same as 0 rotation, so you should not repeat. Good, but there's a trickier question. Can anybody tell me? In hat, which direction does it point in? Does it point in this direction or in this opposite direction? Or given a rotation, let's use ordinary angles and not radians. Suppose a 270-degree rotation about this axis. Isn't it the same as a 90-degree rotation about this axis? Sorry, not this way.
Yes, sir. The second representation won't be able to do this. It has to be minus in some sense.
Minus in what sense?
I mean to reverse
90 degree and
the
270?
second representation. Yes, sir. Yep.
Yeah, but n hat is a unit vector, right? And for angles, of course, or for numbers, you can say something is positive, something is negative, something is 0. For vectors, you can't say this is a positive vector, that's a negative vector. Makes no sense, right?
Yes.
All I'm saying is, of course, these are inverses of each other. One is n hat, the other is minus n hat. But you cannot say that I will only take the positive unit vector, not the negative unit vector, because there is no sense to that. There is no such thing as a positive unit vector. Both unit vectors are equally good. And somebody else could have said, okay, no, this rotation is not 270 degrees about 270 degrees about the axis. It's actually 90 degrees about the opposite axis. So how would you get out of
theta
that?
modulo 2 pi, if you take the magnitude as theta modulo 2 pi, I think it will work.
No, it will work. Question is, it will actually work with give you too many representations of the same thing. What I'm trying to do, I hope that's clear to everybody. I'm trying to get a one-to-one representation between the set of rotations and some object which I can sort of understand better. That is, instead of the group which is formed by a set of all rotations, I want to represent them by something more concrete. Let's say some vectors. But if I took all vectors in all directions, as you have rightly pointed out, I'm getting the same rotation represented way too many times. But if I allow the rotation angle to go all the way to 360 degrees, to 2 pi, then actually I have the same problem. There is a rotation through n hat through an angle theta, and a rotation through minus n hat, about minus n hat, through 2 pi minus theta, are exactly the same rotations.
So then you can split theta to pi instead of 2 pi.
Good. The restriction should be, theta should be restricted to pi. So theta should be allowed to go only up to pi, not beyond that. That way this, so if the moment you get an angle which is more than 180 degrees, let's say you get 190 degrees, you say, okay, it's not really 190 degrees about this axis, it's actually 10 degrees about the opposite axis. And then it's fine. Is that okay? That way you are saving yourselves the problem of having the same rotation being covered multiple times. Is that okay with everybody? But now going back to this theta n hat representation. So what does it really tell you? If you want to use this representation for rotations, what are you doing? You are saying that, okay, I'm taking a vector. Which direction can the vector be in? Any direction, because the axis could be in any direction. And I'm only allowing the length to be anything between 0 and pi. So if you take all such vectors together, what is the geometric object that you get? So if I form the set of all such objects together, where n hat could be anything, any unit vector in 3 dimensions, and theta could be is between 0 and pi. What exactly is this? This is a very simple question. No group theory involved. Okay, nomenclature should be precise. Is it a sphere?
Two sphere.
Two sphere.
The surface of a sphere.
Really? Anybody with a difference of opinion?
So ball.
It will be a
Sir, a ball of radius pi.
Yeah, right.
It will be a solid
Ball,
sphere.
because it's
Is
continuously at
Okay,
0 to
it's
pi.
a ball of radius pi.
Right.
Right? Not a sphere. A sphere is just the when physicists often call something a spherical surface. To a mathematician, the sphere is the surface. A sphere is the set of all points which are at the same distance from the center. So what we call the surface of the sphere is actually the sphere. The proper terminology is ball, and the surface of the ball is the sphere. Okay, here that means okay, if I try to draw this with my rather horrible drawing skills, which is at least supplemented by the fact that the pen automatically corrects for some things. Okay, that was bad anyway. Anyway, this is a sphere that I'm going to draw, and the 3D sphere. Okay, a sphere embedded in 3D, and whose surface is S2. Okay. So you should so it seems that the set of rotation, all rotations, in fact we say the group of all rotations, is pretty simple and straightforward. It's just a ball of radius pi, right? Nothing very complicated about that. A solid ball.
There's an issue here.
Yeah, what's the issue?
You can't make pi closed on both sides, right? Like, that will still, if I take across n cap or minus n cap, a full pi rotation will still give me the same thing. Right?
Okay, great. So, if the set of rotations had been a ball of radius pi, then life would have been very, very easy and rather dull, because the group of rotations would have been rather trivial. And okay, as you will appreciate later perhaps, many of the interesting things that happen in physics, like say the spin half representation and so on, really rely on the fact that this statement is wrong. Okay, not this statement. This statement is right, but the apparent statement that we were making, that this is the set of all rotations, that's actually wrong. Why is it wrong? Because as was pointed out right now, unfortunately this will not work, because n hat pi a point on the surface of this ball, and minus n hat times pi, a point which is right on in the opposite direction. So 2 points, one here and the other maybe here, in the antipodal points, that is exactly in the opposite end of the diameter passing through the center of the sphere. 2 points minus n hat and n hat. So this is minus n hat times pi right on the surface. This one is n hat times pi again on the surface. These 2 points cannot be treated as different points. Okay. So how could we proceed now? If I still want to persist with trying to get a one-to-one connection between rotations and this world?
So we'll have to somehow exclude half of S2 from the ball.
Okay, one possible way as is being. So I hope everybody is following this, right? The ones who are silent, who have trouble understanding this, tell me. One possibility is you. Yeah.
You said this pi n cap and minus pi n cap should not be different.
They are different points on the ball, but they should be the same point on the same rotation, unfortunately. Which is why the ball cannot represent the set of rotations. If I claim that the ball is the set of rotations in mathematicians' language, the problem would be I would end up with 2 different points of the ball, yet they would stand for the same rotation. That, of course, cannot happen. If I'm saying the ball is the set of rotations, then every rotation should correspond to a unique point on the ball, and every point on the ball should correspond to a unique rotation. And that's not happening. So one way out, as has been pointed out, is simply somehow, let's say, take some diameter of the sphere and think of this like peeling a tomato. Let's say you take a tomato, cut the rim, just score the rim and score a circle around the rim and peel off the skin on one side. So you have a skin tomato with skin on the top, tomato without skin on the bottom. That way I'm avoiding the minus n hat pi point. But all other points, say if the length is not pi, any point inside, of course, is a unique rotation. The only problem was with the points on the surface. Okay. So this will work, right? Yes or no? Anybody has any objection to this?
Sir, pi n and minus n with 0, they should correspond to the same rotations?
No, minus n hat with 0 does not correspond to the same rotation. Pi is 180 degrees, not 360. We are not even going to 360 because, as we said, any angle, if the angle exceeds 180, don't use that axis, use the opposite axis. It's a smaller angle.
So this is equivalent of saying take minus pi to plus pi, the theta, instead of 0 to 2 pi.
No, it's not.
No?
It's not.
Okay.
It's not. Just think about it a bit. It's not at all. We are actually pretty close to getting the actual group space. This is called the group space for rotation groups, or for SO3, or group manifold for SO3 if we use big words. I don't really want to use big words right now because that might scare people into thinking that it's more complicated than it is. But the group manifold of SO3, that's what we are trying to build up. And we have nearly got there with this half-skin tomato. But there is still a problem. Can anybody point out what the problem is?
So I'm not sure, but is it at the sort of the place where the hemisphere that we have removed the central sort of dotted line that you've drawn? In that part, sort of one half would have to be closed and the other half would have to be open. Like,
okay, the real problem, as is being pointed out, is that you still have trouble with the hemisphere. because opposite points in the hemisphere would still give you the same rotation. Then you might say, okay, I will take only one half of the hemisphere, so and leave the other half out. But then you will again see that you will have problems with the two edges, two endpoints. Where do you leave them in? Okay, so it's not as simple as just a ball. This fact that n hat pi and minus n hat pi is the same rotations. Now somebody is trying to come in, or did somebody admit that person? Cody or whoever? Anyway, I would ask all of you to join with your Isocol ID, so that is, I don't have to admit anybody. Because especially while I'm giving a presentation, I will not be able to see if somebody wants to come in. Anyway, as I was saying, this whole thing gets complicated because of this fact, this double valuedness on the surface. Okay. So there's a mathematically easier way of doing this instead of skinning a tomato and then trying to keep half of the rim of the edge, drop the other half, and so on. There is an easier way, which is mathematically easier, much more difficult to visualize, which is to say, take a ball of radius pi, as we were doing before, and identify antipodal points on the surface. Now, this is a mathematical thing that I've done here. All we are going to saying really is that, okay, I will take a ball of radius pi, and what I'm going to do is, in addition to taking a ball, I'm going to say, I'm going to impose this condition that these two opposite points are not colored differently any longer, they are the same points. Any 2 points which are opposite, you treat them as the same point. Now, this may sound a bit crazy, but that's something we do all the time. For example, if you take a straight line and then say straight line segment and then say these two endpoints are the same point, what do you end up with?
Circle.
You end up with a circle. So a circle basically is a straight line with two segment with two endpoints identified, or the entire real line with points differing by, say, 2 pi identified with each other. Now, identifying different points and treating them as the same point is a standard mathematical tool. It's called quotienting, or basically establishing equivalence classes. It's done all the time in mathematics. It's not a very big deal for mathematicians, and we are usually used to doing this on some simple scale. But this actually turns out to be quite an interesting thing to do and gives rise to quite non-trivial results. So let me just show you one non-trivial consequence of this. So this is the group manifold of SO3, a set of all rotations. The group manifold is a ball of radius pi with the antipodal points identified. Okay. So I'm going to just show you one consequence of this identification of antipodal points. Why that is of immense physical significance, that we will describe when we come to the Lie group topic later. All I'm trying to show is there are unusual things that can happen here, which is this. Suppose I have a point here, and remember, every point represents a rotation. A point on the surface represents a rotation through an angle pi. A point in the interior of the sphere will represent a rotation through a smaller angle. Now, if I were to draw a loop in the ball, what would that signify? Any idea?
Some series of rotation that leaves the whole thing unchanged. So
no, not the whole thing. Series of rotations, of course, So a loop, of course, is a collection of many points, right? One after the other. So it's a sequence of rotations, which a continuous sequence of rotations, right? Each rotation is very slightly different from the previous rotation. And the end of this entire sequence, you're back to the original rotation. Is that okay with everybody?
Yes, sir.
Yes.
Now, anybody with a confusion about this? Basically, a bunch of points would be a bunch of discrete rotations, but we are saying it's a loop, which means it's a continuous bunch of rotations, which start and end at the same point, which means you're back to zero rotation, not zero rotation, whatever rotation you started with. Okay. Now, think of it this way. Can I now think of another sequence of rotations, each of which are very close to the previous sequence, but somehow they rotate a bit less or differ from each other a bit less? Basically, can I shrink the loop down? And can I do that? If this were an ordinary sphere or ordinary ball and I had a loop drawn on the ball, could I shrink it down?
Yes.
And could I shrink it down even further? And further, until I end up with only one point, which means I have only a single rotation, right? So the point is, if I just had a ball and not this complicated set ball with the ball, but with the opposite points on the surface identified. If I just had a ball, then any loop I drew could be shrunk down to a point. Okay, but on this kind, on SO3, there are actually some kinds of loops like this. Okay, why is this a loop? The loop because this is the point n hat pi. This point is on the surface, and minus n hat pi. So this is a loop, right? Because you're starting from a given rotation, you're slowly moving, slowly changing the rotation, and you have come back to what? The same rotation. There are different points on the ball, but they're the same points on SO3. So with the ball with antipodal points on the surface identified, this point and this point are the same point, which means this is also a loop. Is it clear?
It's a bit abstract.
Is it? What's so abstract about it? Just think about this. You want to start somewhere and end at the same point. That would be a loop without any breaks. Okay. So you can't do this and come back here and call that a loop. A loop has to be you start somewhere, go all the way around, and come back to the same point without any breaks in between, so that you get a sequence of rotations, each of which are very close to the previous step. And at the end of it, you are back to the same rotation. Okay. Here you have a rotation through pi about an axis. Then another rotation, another rotation, another rotation, another rotation. Could be, by the way, this curve need not be on the surface. Could be even a straight line, right joining, could be a diameter, could be something like this, going right in through the sphere and going to the other end. But at any given point, what has happened? Say, for example, if you had a straight line joining n hat pi and minus n hat pi, then what would that mean? You first start with a 180-degree rotation, then you have a slightly smaller rotation about the same axis, then a slightly smaller rotation about the same axis, then a slightly smaller rotation about the same axis. And you keep on doing this. You go to zero rotation, then you go to rotations about the opposite axis, small rotations, slightly bigger, ultimately you end up with. So when you hit the center of the sphere, that's zero rotation. When you're moving on the other side, you're getting slightly bigger rotations until you hit 180-degree rotation about the opposite axis. But 180-degree rotation about this axis and 180 about the opposite axis of the same rotation. So back where you were. So that's why this is a loop.
Sir,
Yeah.
can we think of it in this way? I mean, if we think about the topology of the sphere, then it is not a loop. As in, when you say that when we say a loop on the surface of a sphere, we mean they are like connected. But when we think of it as the topology, the quotient topology of the sphere, I mean, when you are identifying this,
that's exactly what it
then
is.
it is a loop.
That's exactly what it is. It's a quotient topology on the quotient topology, not on the sphere really. It's actually the union of the interior of the sphere and the sphere. So it's basically whatever the B2 open ball B2 is, that is interior union with
yes, sir.
S2 with the quotient topology. So that's a technical term. I just don't want to use the technical terms right now. But all I'm trying to say is, even without those technical terms, you should be able to understand that you started at a rotation, you ended up at the same rotation. So it is a loop, right?
Yes, sir. Yes.
That's all there is to it. But the only important thing here is such a loop, one which starts at a point and ends at the same point, but going to the other side of the sphere. Can you shrink this loop down to a point? Remember, you can't break the loop. It has to stay a loop throughout. But can you shrink it down to a point?
No, sir.
So we can. I mean, you just told for the previous example, you had like a bigger loop and then a smaller loop and then a smaller loop.
Yeah, but how do you get a smaller loop here?
So you go to the. So I guess I'm not sure.
No, remember, it has to stay a loop, right? Okay. Is that okay? That is important. It has to stay a loop. Now, if you detach it from, suppose it's going right in. Let's say this is a straight line. Can I shrink it down? The moment I shrink it by detaching this point, what happens? It's no longer a loop, right? It's not going from, say, suppose instead of the straight line going from minus n hat pi to plus n hat pi. So let's make it slightly shorter. So you don't take the entire straight line, you take the straight line from here to here. That could be done infinitesimally. The trouble is, if you do this, is this a loop any longer? It's minus.
It's not a loop connecting n pi and minus.
Okay, let's call this plus this minus anyway. But this is plus n hat times some pi minus epsilon, and this is minus n hat times pi minus epsilon. But these 2 points are not the same, right? Any longer. It's only n hat pi and minus n hat pi which are the same points. If you move slightly in, it's no longer the same. These two opposite ends are no longer the same point. Yeah. So what has happened is that earlier you were starting somewhere, coming back there. That's what a loop does. Now you're not starting and ending at the same point. So it's no longer a loop. It is just a broken curve like this. Okay. Remember, the question was, can I shrink the loop to a point without breaking it? Doing it continuously without breaking it. That I cannot do to this. Because, okay, if you tried sticking to the surface so that that problem doesn't arise, but move the point. Let's say you try to move this closer to the other point. Okay. But if I move this point, in order to stay a loop, the other end has to move to the opposite point on the sphere surface. Otherwise, it will not be a loop any longer, right? So if you try to move this until you get close to this and then manage to shrink it, you simply can't, because the moment you move this end, to stay a loop, the other end also has to move to the opposite point. Okay. Clear?
Yes.
So one question here, like this property that we are talking about of shrinking the loop, like it is at this point, it's just some arbitrary property that we picked up and we are showing that this specific set or this thing doesn't have it. But is there any reason why we should consider this ability to shrink closed loops to a point an important?
Well, first, there are two reasons why they are very important. One of them is more abstract and mathematical. There's something called the fundamental group for a topological space. But that would be something we would have covered in the algebraic topology course if we had one. We do have one, right? There's a mathematical phase course. The advanced mathematical physics has algebraic topology in it. There you would realize that what I'm talking about really is the fundamental group of this particular space. Since I'm not going to teach you algebraic topology, I'm not going to use that language. Okay, that's one mathematical reason. In fact, it's a very important reason. One important thing is this clearly shows that the ball and what we have here are two entirely different entities. On a ball, every loop can be shrunk to a point. Here, every loop can't be. Okay, so topologically, at least global property wise, they're different. But that's not the aim of why I'm talking about this. Of course, there's a very direct physical significance to that. But that, as I said, will come in the later half of the course when we talk about representations of the rotation group. But let me just give you the answer right now. You all know this, right? There are things called spinors, things which describe spin-half systems. Technically, they furnish something called a spinor representation of the rotation group. Okay, you may not have heard these words used, but the spinor representation of the rotation group is exactly why there are spin-half particles in the universe, which, as you would all agree, is a very, very important thing for physics, right? After all matter is made of spin-half particles, at least all observable matter. But the spinor representation of the rotation group exists specifically because of this property of the rotation group, the fact that it's not simply connected. That's a technical term, that there are loops which you can't shrink to a point. So this has immense physical significance. It's just that I'm not in a position to explain what the physical significance is right now. I'm just showing you the mathematical aspect of it, trying not to use technical language, or at least trying not to use technical language unless you force me to. But what this this quotienting, etc., essentially means that you identify opposite points on the sphere. Saying that the fundamental group of this space is non-trivial simply means that there are loops in this space which can't be shrunk to a point. Okay. Okay, let me just continue with this a bit and let me show you one more important result, which is in line with this non-shrinkability of some loops. Of course, a loop which starts at the surface and ends at the surface, like this. This one can definitely be shrunk to a point, right? All you have to do is just but this is a loop of this ordinary kind. This can be shrunk to a point, but this is a loop also, and this can't be shrunk to a point. Okay. Is everybody completely confused about this, or is this okay?
But this is the normal Euclidean sphere, right?
No, there's not a normal Euclidean sphere. On a normal Euclidean sphere, this wouldn't have been a loop. On a normal Euclidean sphere, all loops can be shrunk. I'm again talking about the SO3 space. Yeah. On normal Euclidean sphere, these can be shrunk to a point. This one is not even a loop, so why would we even bother talking about it? Okay, I'm only asking, can loops be shrunk to a point? Why am I asking that question? Why is that a deep mathematical and physical question to ask? Is something I'm not going to talk about right now. Let's just assume it is. And I've told you why. I've told you that the reason is somehow spin-half. The very existence of the universe depends on this. Okay. But why is that? That connection I can't make right now. We have not gone to that stage of the course as yet. After all, we have just started, right? We cannot really talk about something which will come to near the end. But the question I have for you is this. Why is this a loop? The answer is on my space, the opposite points are the same points. Opposite points on the sphere are actually identified. They're the same point. So this is a loop. And this loop cannot be shrunk to a point. Okay. But this loop cannot be shrunk to a point. Okay, let's use another color. This is another loop which cannot be shrunk to a point, right? But if you think of composing the loops by taking one loop after another, that is going this way and then traversing this, now you realize that you get a loop which is actually a double loop, right? You have gone twice round the thing. But this double loop can easily be shrunk to a point by doing this. Which is to say, okay, this is something which may take some amount of effort to realize. The fact that there are loops which cannot be shrunk to a point, that's encoded in the jargon by saying that SO3 is multiply connected. Not simply connected means multiply connected. But here you have a special situation. If you have to take two loops of this kind and just join them together, you end up with the identity, with something which can be shrunk to a point. Okay? So SO3 has this very special property, which is why, okay, by the way, this is something, the consequence of this is something which you all definitely know. At least I am hoping all of you know. That is, if I did a 2 pi rotation, is it the same thing as doing no rotation at all? So if I take a spin half system with whatever, you remember what the spin half system's rotation operators are, right? Say for the z axis, it would simply be, there's the operator which will act on a spin half system, right? And that will rotate the object. If theta is 2 pi, is this identity?
No.
For theta equals 2 pi, this is actually negative of the identity. Okay. Which is why a 2 pi rotation on a spin-off object gives you back not the original spinner, original two-component object that describes the spin, but it's negative. Of course, we can say that has no physical significance because the mod square is all that matters, so the minus sign cancels out. That's true. But it is a fact that you have a representation in which the two-component object does not return to its own value. When you rotate through 2 pi, it returns to its negative. But if you do it twice, what happens? There's a 4 pi rotation. 4 pi, if theta is 4 pi, then this rotation operator is always the identity. So 2 pi rotations are actually different from 0 rotations, but 4 pi rotations are identical to 0 rotations. This is a very deep thing which allows us to have spin-half representations at all. Why? Okay, this is also be a teaser for the rest of the course, not the rest of the course, at least for our topic of SO3 when we come to it. There you will see the physical reason why not really the physical reason, the mathematical reason why spin half is connected to this SO3 being doubly connected. But I'm pretty sure all of you have, okay, not all of you, but most of you may have already seen this. At least look up on YouTube if you have not seen this before. The Feynman belt trick, or something which you can do with a cup in your hand. You can do it yourself. But unfortunately, I don't have the camera connected to my laptop right now. Otherwise I would have been able to perhaps show you that. That is, if you hold the cup in your hand and try turning the cup through 2 pi, you'll find that at the end the cup may have come back to whatever position it had. If you have a cup handy, an empty cup, not a cup with liquid in it right now, you can easily try doing this and convince yourself. If you turn the cup to 2 pi, your wrist, etc., will end up being in a rather twisted position at the end. So the cup may have come back to where it was, but the world itself has not. Your arm gets rather badly twisted in the process. But if you turn it through another 2 pi, you can actually show, you can continuously turn it through another 2 pi and get everything back, including your hand, to where it was before. If you can't figure that out, I would urge that you try doing it yourself. Perhaps with an unbreakable cup, and definitely not with an empty cup, not with liquid in it. So, but this is an experiment which you can try at home. And if you can't figure out what I'm talking about even after doing it, what you should do is go on YouTube, look up the Feynman belt trick or Feynman cup trick. There are many names under which this goes. And there you will see that why this 2 pi rotation and 4 pi, why 4 pi rotation is actually identity and 2 pi rotation is not. Okay. And the whole mathematical reason behind this is the fact that SO3 is doubly connected. Okay. But to quickly end this, I'm going to take only 10 more minutes today. This is something which I would ask all of you to try yourselves. Is there any question about this? Apart from the deep question as to how this connects with physics and so on. What I've said so far is that, does that make sense?
Sir, when you are talking about 2 pi and 4 pi rotations, you are talking about in the SO3 manifold, SO3 group space, not in the real space rotation, right?
I'm talking about real space rotations, definitely. Because SO3 group, the SO3 group manifold is just a way of representing real space rotations. Every point on the SO3 group manifold represents a rotation in real 3D space. Yeah, that's exactly what I'm talking about. If an object is connected to the outside world, then rotating it through 2 pi leaves an imprint on the outside world, which you cannot undo continuously. But if the same object can be rotated through 4 pi, which can, and in such a way that the effect on its outside world can be continuously undone. So that's why if you're holding the cup in your hand, you just turn the cup through 2 pi, ask people to shut their eyes before and after. You will not be able to tell the difference. But if you try holding the cup in your hand and turning it through 2 pi, unless you happen to have exactly rubbery arms, I'm pretty sure you will be able to tell the difference. Continuously. Continuously is important. You are not allowed to turn the cup and then leave it and then hold it again and turn it. Okay. Just hold the cup in your wrist and try turning your hand continuously so that the cup turns to 2 pi. In fact, you will find it impossible to do without tilting your hand somehow, because otherwise your wrist will break. But at the end of the thing, you will be able to turn the whole thing around with your arm twisted exactly opposite. So, while the object itself stays identical to what it was, your arm is will be in a very uncomfortable twisted position at the end of it. Remember, you are allowed to do it continuously. You are not allowed to leave the cup in the middle and then hold it again after turning it. Just try it. It's very simple. You will sort of look like Muthaiya Muralidharan trying to come into bowl or something in the process. If you're too young to know who Muthaiya Muralidharan is, I apologize. But I'm sure people have not forgotten legends of cricket that early, this soon. So anybody who has seen Muthaiya Muralidharan bowl would know what I'm talking about. Or you would just try holding a cup in your hand and try turning it to 180 degrees without letting go of the cup. You would know what I'm talking about. And then it will take a bit of effort, and don't overstrain yourself. You may even injure yourself if you try too hard. But if you figure it out the right way, you can actually turn it through 2 pi again pretty easily. But moving your arms around a bit, so that at the end of the day, the curve will turn through 4 pi and your arm will be back where it was at the beginning with no additional twists or stresses. I would urge you to try it. There's an experiment, and that's a real rotation I'm talking about. I'm not talking about abstract rotations in a group manifold. And the whole point is every point on this group manifold stands for a real rotation. It's not an abstract mathematical thing in that sense. But in order that it become a one-to-one correspondence, you end up with this rather abstract sounding effect, a sounding space. Okay. So the group of all rotations is not really a very simple set. It is a rather complicated set that way. It has a rather non-trivial topology. That's a technical term you use here. And the non-trivial topology is actually quite interesting and it's not a trivial mathematical curiosity. It has immense physical significance. Anyway, for those of you who are getting scared by this, please don't be, because this is something we are going to discuss in great detail later on in the course when we actually come to this. Okay. Here I'm just answering this question about SO3 and SUN being the same, or similar. So I just wanted to show you one important way in which they're different. So let's just quickly talk to you about the SU2. You will later see that there's a deep connection between SU2 and SO3. In fact, you already know that there's a connection. At least those of you who have done quantum mechanics with spin half particles should have seen that, whereas we're talking of rotating a spinner, what you do is applying a SU2 operator on it. But the deeper mathematical connections we'll talk about later. For the time being, let me just remind you what SU2 is. Everybody here knows what SU2 is, right? Anybody here who hasn't heard SU2 before? Well, I'm assuming everybody understands what SU2 is, at least nomenclature-wise. So SU2, of course, is a set of 2 by 2 unitary matrices. Okay. And if you have any 2 by 2 complex matrix, to be unitary, what has to happen is that it's adjoint, Hermitian adjoint, which is alpha star, delta star, gamma star, beta star, right? You transpose and complex conjugate, right? This has to be the same as its inverse. Now, one very important rule in maths is, or one important trick in maths, is to figure out how to invert a 2 by 2 matrix. By the way, one of my ex-students had actually gone on record saying that this is the only useful thing that I had ever taught him. He didn't say only useful thing, but he did say this is the most useful thing that I taught him. So the useful thing is this: how do you invert a 2 by 2 matrix? The rule is you just flip the diagonal terms, change the sign of the off-diagonal terms, and divide by the determinant. This, of course, is not a very deep rule. You can easily figure out why this is the case. It's just the standard adjugate matrix divided by determinant thing. But for 2 by 2, it becomes very, very simple. The rule is just flip the diagonals and change the sign of the off-diagonals. That's it. And not that's it, you have to divide by the determinant. But for SU2, S stands for special unitary, that is determinant 1. So this factor is not there. So if for every SU2 matrix has to satisfy this, it's made out of 4 complex numbers, alpha, beta, gamma, and delta. But this matrix, the inverse, has to be the same as this matrix, which is the Hermitian adjoint. And that immediately tells you the delta must be alpha conjugate and gamma must be minus beta star. I'm pretty sure most of you also already knew this, but still. So every SU2 matrix has to be of this form, with the additional constraint that alpha mod square plus beta mod square equals 1. Is this already familiar to everybody? I am there, right?
Yes, sir. So
Yes, sir.
something like this was done in one of the math course in the second year. I mean, that course was on the
Okay, so this is familiar. So all SU2 matrices, in fact, you can easily show that there's a one-to-one correspondence between all matrices of this shape and the set SU2. That is, every SU2 matrix is of this type, and every matrix which has this structure, alpha beta minus beta star alpha star, is an SU2 matrix. Fine. But now we come to one important point. What does this mean? That means that every SU2 matrix element can be written in terms of two complex numbers alpha and beta, and that's it. You give me two complex numbers alpha and beta, I give you an SU2 matrix, right? But not any two arbitrary complex numbers. Those complex numbers have to satisfy this condition. So if you think of alpha and beta as complex numbers, you can also, of course, think of them as pair of real numbers, right? So SU2 can be put in one-to-one correspondence with 4 real numbers, but these real numbers are not independent of each other. They have to satisfy the condition. That's alpha mod square. This is beta mod square, right? You add them together, what do you get? So SU2's group manifold, the set of all points which are in one-to-one correspondence to SU2, is what? What is this? Set of 4 real numbers satisfying this condition. What object is this? This is the three-dimensional sphere. S3, of course, is a sphere which is embedded in 4 dimensions. Okay. But it's very simple to prove that every sphere is simply connected. That is, you take a loop on the surface of a sphere, you can always shrink it down to a point. What that means is while SO3 is doubly connected, so has a rather non-trivial topological feature that way, SU2 is simply connected. Not only that, SU2 actually is homomorphic to SO3. That's again a technical term which we will explain later. But in a sense, they have very similar group properties. But SU2 is simpler because of being simply connected, and which is why there are many interesting. In fact, that is what we exploit a lot of times. We actually use SU2 over and over again when we try to find out things about rotations. SU2 is actually easier to do mathematically than SO3 is. So the answer to the original question, is SO3 the same as SU2? The answer is no. They are groups. They are very similar to each other. In some respects, they are very, very dissimilar in other respects. And this dissimilarity actually is very important physically. Now, I don't expect everybody to understand everything of what I said right now. That's not necessary because A, this is way, way beyond what we were discussing so far. And B, because we are going to repeat this again later on with more direct physical consequences demonstrated. Hopefully, this issue will be clearer then. But in the meantime, I would urge all of you to do this. Try twisting a cup in your hand through 2 pi and 4 pi and see whether you can bring your hand back to where it was. Without, of course, untwist. So you have to keep the cup twist it through 2 pi and bring your hand back. You'll find that that's impossible to do. Unless you can detach your hand and fix it back again. But what's even more interesting is that you will find that if you try doing it, the statement that 2 pi rotation is not the same as no rotation at all will turn out to be rather trivial. It turns out to be very easy to understand. What may be even less easy to understand is if you do it twice, you can actually undo what you did to your hand. And if you have not seen this before, definitely look up the Feynman-Bell trick on the net. There are plenty of videos which show you exactly. Even there are plenty of videos which uses a belt, and there are videos which uses a cup. But before you do that, it's better to try it out yourself first. So, any questions? Any less complicated questions? It is about whatever we have. I'm assuming from the fact that nobody asked any questions about what we covered so far, or at least apart from a very few questions at the beginning, whatever is there in lectures 1 and 2 was easy enough to understand. By the way, this class is primarily meant for that, not for asking deep questions about the connection between physics and mathematics. That we will handle on the way. But the main aim of this class is to ensure that whatever was discussed in the videos, if something is unclear, ask that, let's talk it over, and whatever problems we have, we will try to discuss that with you. Whatever our problem says, that's the second part. So I'm assuming everything is clear so far. It should be, because we have only covered very trivial stuff so far. Although, okay, let me ask for an honest answer. How many of you actually could figure out the answer to question 3 in the first problem set without going on the net and finding out the answer? Or I'm leaving aside those of you who had done this before in the DMS course. That is the question which said left identity, left inverse is alone enough to define a group. Okay, Akhil managed to do it himself. Good. I'm not saying that looking up the net is bad. As long as you understand what you find there. Look, assignments, frankly, is not really a gradation thing. Okay, quite a few. Good. Assignments are primarily meant for understanding. So if you have to discuss among yourselves, look up the net, by all means do that. But at the end of the day, make sure that you have understood what you are writing. And let me warn you, there will be vivas from time to time during the course. And yeah, I looked at the net and I messed up in between. Very good. You can, of course, the best idea would be try it first. If you mess it up, most of the answers will be there on the net. The trouble is, some of the answers will be very non-trivial, and most things that you will find in net may be way too difficult to sort of fit in with the rest of the course. Because, well, especially when a mathematician answers a group theory question, the aim is to be as general as possible. Say, for example, later on when we do group representations, we're only going to talk about linear representations on real numbers and complex numbers at most. Mathematicians would talk about all kinds of representations over modules, over various kinds of fields, and so on. And that's essential for their purpose. Since it's not essential for us, we will only do the easiest things.
Sir.
Yeah.
Sir.
Yes.
Here, when you represented SO3 using identification of the antipodal points.
Yeah.
Before that, you were doing that by another approach, right? Means
No, I was
peeling
not
off
going
one
by
of the
another approach.
hemisphere.
Right. I was just showing that approach is not complete.
Means why is it not complete? I didn't understand.
Which one? Okay, this point if you just took the sphere without the antipodal points identified. Is that your question?
Yes, yes.
The point is, when you say this is a set which represents the group, or I want one-to-one correspondence between every point in this set and every point in the group, every element of the group. Okay? Is that clear?
Yes,
And
sir.
one-to-one
Yes, yes.
correspondence means every point in the group, every element of the group should have a unique point here, and the point has to be unique.
Yes, yes.
So here the problem is, if you take a sphere of radius pi, of course, will not do. That will only give you pi rotations. You need a ball of radius pi. Okay? All smaller rotations as well. With smaller rotations, there's no problem. But once you get on the surface of the sphere, this point and this point, there are two different points on the sphere, right? But what do they represent? They both represent 180-degree rotations about opposite axis, n and minus n, but 180-degree rotations. Now, if you rotate by 180 degree through n, you get exactly the same rotation as rotating through 180 degree about minus n.
Yes, yes.
That is why you have to identify the two. So without that identification,
Then suppose you just suppose keep the upper half of the sphere and delete the lower half of the sphere, as you mentioned before.
So you skin the tomato, right? You just not the
yes,
you,
yes.
You leave the ball in. So then on the ring, I will have a hemisphere right here. On the hemisphere, there will be opposite points which are the same.
So I delete one side of the ring then.
Then you will have two endpoints, right?
Then I delete one endpoint.
Yeah, that can be done. But will that be easier to discuss than what I talked about?
No, but the point is, when you do this, then this does not look that it isn't simply connected, right? Means doing this operation, what we get, that is simply connected.
It's actually still multiply connected. It's just much more difficult to understand. This one is still multiply connected because it's exactly the same space.
I don't understand that.
Yeah, that's way more difficult to understand. That's why I avoided that.
Sir, this sort of representation wouldn't be unique, right? Like, no. I can choose the n cap at which I delete a point.
No,
so I don't know. Will that make a difference to our purposes?
Tomato thing will not be a unique representation. There would be many ways of doing it, depending on which half of the skin you want to strip. But you didn't want don't want the representation to be unique. You want, once you have a representation, you want a one-to-one correspondence. That is not a problem there. The problem is this one will be way more complicated, especially you will have very great difficulties in trying to talk about continuous changes here. Because, for example, if you go from here to here, then what do? You have to jump back from the other side, right? And that would be would look like a discontinuous change, whereas it's actually a continuous change. And that would actually that is the reason why you are finding difficulty understanding why this is multiply connected, because continuous loops are difficult to see here. A loop which goes like this, comes down to the equator and then starts off on the other side, is actually a loop. But more importantly, it's also continuous. This one doesn't look continuous at all. So this representation would actually make it very difficult to understand whether something is continuous or not. And which is why you would be having difficulty in understanding why this is multiply connected. The ball with opposite points identified has continuity, there's no issue with that. So simply connected or not is difficult to understand here, simply because continuity is difficult to intuitively understand here.
Okay, sir.
Okay. Anyway, I'm getting a call right now, and this is nice time to wind up the course as well. Wind up today's lecture, not course. Okay. So bye for today. Next day we will meet again at 12. Okay.